Good day. So today we're going to be discussing about Thevenin theorem. Thevenin theorem states that any two-terminal linear network may be represented by a series combination of a voltage source and a resistor. The value of the voltage source is the voltage that appears across the open circuited terminal. The value of the resistance is the equivalent resistance seen looking back into the network with all energy sources replaced by their respective internal resistance. So this theorem encompasses everything you need to know about the Thevenin. So for example, if we have a simple circuit like this, so one thing you should know that Thevenin theorem is only applied in a two-terminal network. Any network that has two terminals, just like this one, you can call it A, B, a two-terminal network. So Thevenin theorem is trying to tell us that in a network like this, it can be represented by a series combination of a voltage source, and the voltage source is the voltage that appears across this open terminal. So Thevenin voltage is the voltage that appears across this open terminal. It can be called ETH or VTH, meaning Thevenin voltage. Then the resistance is a single resistance gotten looking back into the network. So actually what it actually means is that we'll find the equivalent resistance of all these resistances, which will make up the Thevenin resistance. So Thevenin theorem is now saying that this network can be represented to give us just a voltage and a resistor in series. So we'll have something like this, ETH, something like this. I forgot to add this here. RTH. So this is the Thevenin equivalent circuit. So as you can see, Thevenin theorem is used in simplifying complex networks. Just imagine a network you have more than 20 resistances of and 50, or let's say 15 voltage sources. So Thevenin theorem is just used to simplify that complex network into just a single combination of a voltage source, one voltage source and one resistor, to make it better for efficient calculation in the network. Okay, so we have an example said, determine the Thevenin equivalent circuit of the figure below, given that E is equals to 16.2 volts, R1 is equals to 3 kilo ohms, R2 is equals to 8 kilo ohms, and R3 is equals to 4 kilo ohms. So from the figure below, we can see that these two circles here, it determines the two terminal. So this is a two-terminal network. So when simplifying using Thevenin theorem, we will not actually need the load at the start. So in doing so, we will just rewrite this down. So this is the two-terminal network. So in finding the Thevenin equivalent circuits, the two basic things we need to find is the Thevenin voltage, VTH, and the Thevenin resistance, RTH. When we find these two, we have gotten everything we need to find the Thevenin equivalent circuit. So to find the Thevenin voltage, and as I said, the Thevenin voltage is from the theorem that I said earlier. It is the voltage that appears across the open circuited terminal, ETH. It is the voltage that appears across this open circuited terminal. And from practicals, it can be seen that it is the voltage that appears across this R2 resistor, because it is in parallel with the Thevenin voltage. So to find the Thevenin voltage, we're actually looking for the voltage that appears across this R2, that appears across this terminal, because we can see that here, they are almost the same. So we are looking to find the voltage, Thevenin voltage, we are looking for the voltage that appears across R2. So using the voltage divider rule, we can say that, let's call V2 the voltage appearing across the R2 resistor. So using voltage divider, we can say that V2 is equals to R2 over R1 plus R2 times E. So this is giving us R2 is 8 over R1 is 3 plus 8, 3 plus 8 times E is 16.72, 16.72. So we'll be getting so that is 8 over 11 times 16.72. This is equals to 12.16 volts. So therefore, V2 is also equals to VTH, which is equals to 12.16 volts. So we have gotten our Thevenin voltage. Then to get our Thevenin resistance, we would have to draw the circuit again. But this time, from the theorem, it said that you will replace all energy sources with their respective internal resistance. So we can see that this is an energy source. So what it means is that we replace this energy source by its internal resistance. And from the question given, the energy source E does not have any internal resistance. So we automatically assume it to be 0 ohms. That is 0 resistance. So in so doing, we need to redraw it to get the correct diagram. So we're going to replace that energy source with 0 internal resistance. That is just an empty wire since it does not have any resistance. Then from the theorem I said, Thevenin resistance is the resistance seen looking back into the network. Looking back into the network. Later on, you'll find out how important this is. The resistance is calculated looking back into the network. So we have R1, R2, and R3. So Thevenin resistance is just finding the total resistance. So as we can see, there's something I usually use to determine how to find this equivalent resistance. We can see that as let's assume that current is flowing through this point, this place, R3. We can see that when the current comes to this junction, it divides. It divides into I1 and I2. Let's call here I3, here is I1 and I2. So any place the current divides, it shows that those two parts are in parallel and they will end up coming to meet to make up that I3 here. So RTH is equals to R3 parallel, sorry, RTH is equals to R3 plus R1 parallel to R2. So you get it because R1 and R2 are sharing I3. So we can see that they're actually in parallel to each other because they're sharing the same current. So we can say that R3 and our R3 is 4 kilo ohm, R2 8 kilo ohm, R1 3 kilo ohm. Let me just write it down so I will not forget. R1 is equal to 3 kilo ohm, R2 is equal to 8 kilo ohm, R3 is equal to 4 kilo ohm. So that will be 4 plus 3 times 8 over 3 plus 8. This is equal to 4 plus 3 times 8 is 24 over 11. So we'll be having 6.18 kilo ohms. So our Thevenin resistance is equal to 6.18 kilo ohm and our Thevenin voltage is equal to 12.16 volts. So in drawing the Thevenin equivalent circuits, so now we have represented these resistances by a single resistor, that is the Thevenin voltage, and we have represented the voltage source by a single voltage source called the VTH. So in drawing it, we will just need to bring out the Thevenin voltage just like this. then a Thevenin resistance, then the load. So Thevenin voltage VTH is equals to 12.16 volts. Thevenin resistance is equals to 6.18 kilo ohm. Then this is our load. So this is the Thevenin equivalent circuit. So as we can see, we just simplified this quite complex circuit into a circuit of just a single voltage source and a resistor.